Okay, so thank you for inviting me, for having me. As said, I'm from Ghent, and I think most of you know Belgium, but Ghent is maybe less well known. Well, you all know Brussels, because everything that goes wrong in your country, you blame it to Brussels. Capital of Belgium, also capital of Europe, NATO headquarters, so everybody knows that. Well, Ghent is a town that's about 60 kilometers northwest of Brussels, in the Flemish region, and it is actually a very beautiful medieval town. So if you ever have the chance of visiting it, please do so. We are a relatively small institute, and we're all focusing our research on galaxies. So we try to find out what are galaxies, how do they evolve into the structures we see today. And so they're very beautiful things. This is like an infrared galaxy that most people have seen, the James Webb instrument image. And so we all try to find out where do they come from, how do they evolve. And there are several clues that we want to investigate. For example, there's a huge diversity in galaxy morphology. You have, the Hubble tuning fork. You have galaxies that are completely roundish without a lot of structure. You have galaxies that are very clumpy and spirally and even less regular than that. One thing we want to investigate is why do we have these different structures? Where does that come from? And can we explain also how different physical parameters of galaxies vary systematically along the sequence? You need to see, like, the ones that are a bit featureless are more yellowish, reddish. The ones that are irregular are blue. How can we explain that? We also want to find out or try to explain the population statistics of galaxies, like how many galaxies are there of each type, or even correlations among them. So this is the well-known diagram between the horizontal axis stellar mass, the vertical axis is color, and you see there's two major galaxy populations. You have here the blue cloud. These are relatively blue, not so massive galaxies, typically small spiral galaxies. Then you have the red sequence. These are the elliptical redder galaxies. So why do we have this bimodality? Can we explain that from physical principles? Something we try to find out. Also, there's a lot of scaling relations in galaxies. That means we have a lot of correlations between different physical parameters which are not expected a priori. For example, here you have the Fisher relation on your left. That is a correlation between, here this is just the luminosity, so the intrinsic brightness of a galaxy. This is the width of the H1 line. It's actually a measure for the dark matter mass. So these two correlate. Why is that? It's not that clear a priori. On the right, you have a relation between stellar mass and metallicity, meaning that more massive galaxies appear to be more metal-rich. And there's a secondary parameter then, that's the star formation. So all of these correlations, can we find out how that goes? And then, now that we have a lot of observations going even into like high redshift, we can measure certain aspects of the galaxy population directly. For example, what you see here is the redshift evolution of galaxy sizes, meaning on average, galaxies were smaller in the past and are bigger today. So they evolve into a population that they essentially grow in size, and according to a certain systematic way. Question is, can we explain that? So what we are looking at, and not just us, of course, but the whole extragalactic community, is a theory of galaxy formation and evolution that explains essentially all of these observations. Now, that is not so simple, because galaxies are very complex structures, and one way to do that, and that is the way that is currently maybe the most popular way to try and do that, is through hydrodynamic simulations. So cosmological hydrodynamic simulations where you try to follow the formation of not a single galaxy, but a whole population of galaxies through more or less first principles. So you try to find out what are the physical properties or physical recipes, physical methods that are applicable in galaxy evolution. You have gravity, you have hydrodynamics, you have magnetic fields, you have cosmic rays, then you have feedback by black holes, feedback by supernovae. You try to put it all in the computer and let it run for several months. And the hope is that at the end, you come up with a universe, a mock universe full of things that look like the galaxy population we have. And this is a field that has been evolving quite dramatically in the past decade, I would say. Until 10 years ago, people were not capable of making realistic galaxies. And now this works better and better. I was not involved in this. I stole this from someone else. But there are now a number of projects, large projects, where people manage to reproduce reasonable galaxy populations. And you have some of the what we call big volume simulations. These are parts of the universe, typically about 100 megaparsecs on the side. So these are relatively big boxes with thousands of galaxies. And you try to reproduce the galaxy population at large. You try to get the right number of massive galaxies versus small galaxies, red versus blue galaxies, and so on. And on the right here, you see zoom simulations. So these are simulations of smaller volumes, but then you have higher resolution, and you try to get the detailed properties of the galaxies in a better way. And so most of what you see here are all simulations of the last, say, 5 years, because it's really a field that has evolved amazingly. Now, so what do we do? Well, there's a fundamental problem if you have a cosmological simulation, because what you end up with is like a list of particles or cells in 3D with given masses, temperatures, metallicities, ages, and so on. But what you see in observations, if you look through your telescope, you have your 2D distribution of light on the plane of the sky. You have your observations in optical or X-rays or infrared. Now you have to try to match these two, but they're not necessarily one-to-one, because a 3D distribution of stars does not easily translate to an image on the sky. And so what you have to do is make realistic mock observations from your simulated galaxies. So from your particle-based things, try to create an image that you can then compare to observations. And you can do that in a relatively simple way by just saying, well, I place my detector here and every particle just radiates to my detector, and then you create images like this. But there's a number of problems, and one of them is the presence of interstellar dust. And this is an image of Andromeda, our neighbor. And you see you have blue stars in the outskirts and more reddish stars in the center. But then you have these dark patches here. These are dust lanes. And dust are very tiny particles, talking about a tenth of a micron, so very small. There's not that much dust in the galaxy. Typically, the dust to gas ratio is 100. So there's 1/100. So there's 100 times more gas than there is dust. So it's really not that much. But it does affect the way a galaxy looks quite drastically. Because this is the same galaxy, but now taken in the far infrared with Herschel. And if you compare these two, see here, there where there were dark lanes in the optical image, and go back, you see these dark lanes. Now they really are very bright here in the infrared. That is because these dust grains, they re-radiate the light they absorbed, and they re-radiate in the infrared. And you can say that's not that bad, because it's not that much. There's not so much dust. This is combined image, but actually it is quite a lot. But if you look at a typical SED, spectral energy distribution of a galaxy, it's the total amount of power emitted as a function of wavelength. What you would see if there were no dust would be the blue curve. So this is just all the stars that emit. They're typically more or less black bodies. So that's the intrinsic spectrum of a galaxy. Now, if you add dust to this galaxy, the SED you get is the red one. It's completely different. And especially in the UV optical, you have serious attenuation by dust. So dust eats away part of the starlight. And in the mid-infrared, far-infrared millimeter, the emission is completely dominated by dust emission. So even if there's not much dust, it affects the galaxy or the way it looks completely. And so that is essentially what we started to do with SCIR. That's what we wanted to do, is develop a piece of code, software, where you can calculate this interaction between starlight and dust grains in a realistic setting. And in a realistic setting means, of course, in 3D. And it's quite a difficult problem, radiative transfer, because it is very nonlinear, very non-local. So you have to do it numerically. And the way we do that is using the Monte Carlo method. And so we started working on this more than 20 years ago, and it has developed in quite a big code by now. I'll come back to what we can do with SCIR beyond this, what we call radiative transfer post-processing of simulated galaxies at the end of the talk. But if we apply it to the problem I was mentioning, you start with, say, a galaxy from, or it's not a galaxy, it's like a list of particles and cells from a hydro simulation. Typically, like one of these galaxies is 10 million star particles and 1 million dust cells, something like that. We take all of these particles and cells and convert them and assign spectral energy distributions to them and turn it into input for SCIR. Then we put it on a grid. So we have our medium that we divide into small little cells with more cells where there's more dust and so on. We set up instruments where we want and with the characteristics that we want. We push the button, and ideally what you end up with is a set of images at different wavelengths. Here it's going from UV to infrared images. Okay, so and that is a methodology that we developed some 10 years ago, and that has been refined and optimized for years. And you can use that to test a number of cosmological simulations and compare them to observations in a way where we think this is really an apples-to-apples comparison. One thing we can do is look at fluxes. So just look at the whole galaxy, how much light comes out of this galaxy. If you do that at different wavelengths, you end up with what we call an SED. And this has been done for really 10,000s of galaxies from cosmological simulations. So we applied it to EGLE, to TNG, to Auriga, and so on. This is relatively cheap. So you can do that, you run that on a decent computer. Within half an hour, you can have such an SED. So you can do that for, if you have a big computer, you can do it for tens of thousands of galaxies if you have them. And you look, for example, the SEDs you have here. The bottom one is an observed galaxy from the Wikipedia sample. The top one, the two top ones are two simulated galaxies from two different EGLE runs. And see on average or globally, it looks a bit similar, but there are also some differences. And so the idea of what we want to do is really try to find to which degree there are similarities, but we are definitely interested in the differences. That tells us something on what could possibly be wrong.
The black line is a SCIR model, or?
The black line is an SED fit through the broadband fluxes. So we can also generate this with screen. And one thing we did, for example, is look at this relation that I showed before, like stellar mass versus galaxy color. So this is relatively easy to measure for observed galaxies. And you have that here, the lines or the gray things are like what observers have found in the gamma survey. And indeed, you have like, see here, you have two regions. This is the the red sequence. This is the blue cloud. And now the color is the colored distribution is what comes out of the Eagle simulation. And you see, this is just pure based on the particles, and you see it doesn't agree very well. So you have indeed a little bit of a red sequence, but it's here a lot rather than here. And this one is a bit offset, so it's not that good. Now, if we do it with SKIRT, and we run every galaxy through SKIRT and then compute the colors that way, you see that our blue cloud is now exactly where it should be, and also the red sequence is way more where it should be. So you see a fundamental difference in the colors of galaxies if radiative transfer has been applied appropriately. This is work that we did 5 years ago, also based on our Eagle simulations. So if you have run SKIRT on all Eagle galaxies in a certain volume, and you just add all the power together, you get what we have with cosmic spectral energy distribution. And just the amount of energy emitted as a function of wavelength for a given unit volume in the universe. And we didn't do anything except just summing all of the galaxies SEDs. And this is the agreement. The gray squares are observations based on gamma. You see it agrees pretty well over almost the entire wavelength range. But there are a number of problems. And you see there are, for example, here in the UV, we really have a problem. We have too much UV flux. And also in the infrared, if you don't see it that well here, there are some issues. So, and we believe that comes from the fact that the star-forming regions, which are the main source of UV radiation, that's very difficult to model in these large-scale structures. Okay, so we really need subgrid models to explain like the emission that comes out of star-forming regions. And so we've been working on improving this in our new models. This is a figure from a paper from one of our PhD students that's been submitted, where he looks at the luminosity functions in the local universe. That's just the number of galaxies with a given luminosity in a certain band. This is all the way from far UV to the I band, and if you go down here, it's all the way to the far infrared. I'll go from here. You see the data are again the squares and some of these symbols here. And there's two different models that we plotted here. You have the luminosity functions from the TNG50, that's the purple line, and you have the red is the TNG100. And those are two different cosmological simulations. One of them is a bigger one. TNG100 is a 100 megaparsec volume. The 50 is a 50 megaparsec volume, but with higher resolution. And you see that actually the purple line overestimates the observations in essentially every band. And the red line does a much better job and actually is almost spot on the data. Now, the reason that we found why that is because the subgrid physics that is used to calibrate the TNG cosmological model is calibrated on the 100 megaparsec volume. And so if you use the same subgrid recipes on a higher resolution simulation, actually you over-predict the stellar mass and the star formation rate in your simulations. And the 100 is doing a better job. And you have the same here in the near and far infrared. So it actually, the TNG simulation, the TNG100 really predicts the right number of galaxies in every luminosity bin. which is actually quite a nice thing.
So these are both TNG after processing skirt.
Yes. Yeah. So this comes down to about 10,000 skirt simulations to make these figures. This is from the same paper. These are color relations. So you can look at different colors. For example, here you have R band minus J band. So that's optical infrared. This is U minus R, optical. And you see the comparison. Red is simulations, gray is the data. You see this agrees very well. And you have these two populations of bluer galaxies and redder galaxies. This is RUV minus K versus K minus spire 250, so infrared versus far infrared. Again, this agrees pretty well. We were very happy. But of course, it's much nicer if things do not agree, because then you can learn, try to learn something. And for example, these are two color plots where we do find differences between the model and the observations. So this is galaxy FUV minus NUV, so it's a UV color. And we see that our UV colors are observations, the colors are substantially redder than we have in our model. And so again, this is one of the problems we have. Getting the UV right turns out to be really difficult. And so that's something where we need to work on, and that's not so easy. Here we have something similar. This is the WISE versus spire 250, and this WISE 4 versus spire 250. You see that there is kind of an issue with our mid-infrared. And again, we believe the bulk of the mid-infrared comes from star-forming regions, and that's a little bit the weak point in our post-processing recipe. Now, this is, if you look at global scales, but of course, galaxies are not just single points, they are very complex ecosystems, and we think that what drives galaxy evolution is processes on local scales, so local physical processes. And so if you can compare observations to simulations on local scale, that's a much more powerful test for your galaxy evolution model. And there are different things you can compare on local scales. For example, you look at galaxy morphology. You can look at scaling relations, not just on global scales, but on local scales, on say, kiloparsec scales. You can look at internal kinematics and so on. And for example, what you see here is, this, for example, is a correlation. All the red dots are individual galaxies. It is the dust to stellar mass ratio versus the stellar mass surface density. You see that galaxies form a sequence. But if you look at Andromeda and we look at the same diagnostic, but now on single pixels, you see that every single pixel also belongs to that same sequence, meaning that whatever drives this correlation is not a global process, but is something very local, because it also is on 100 parsec scales, we have the same correlation. Question is, can we also explain this with our radiative transfer model? Now, problem is this computationally much more demanding, because you need to shoot a lot more photons to have a good signal to noise in every pixel. If you just want the global flux, you can do it in half an hour. If you want like a nice image in every band, you're talking about hours. So doing this for a large sample of galaxies is much more demanding. But that doesn't mean we cannot do that. So we were very happy in 2015 when we can do one of them. So we took our largest computer and ran it for several days to make like a sequence of images from different angles. This is one of the first somewhat realistic simulations of spiral galaxy, the Aries simulation. And they simulated only one galaxy at that time. Now they use thousands of galaxies. And this is a simulated optical image, and we can also then calculate how this galaxy would look in the infrared. So on the left, we have optical images at different inclinations. On the right, we have how this galaxy would look if you would observe it with Herschel, for example, in front of it. And then we can start comparing that to observations. And this is what we've been doing in the last few years. So this, for example, is a sample of Auriga galaxies. So Auriga is a simulation, high-resolution simulation suite of Milky Way type galaxies. And here you see an overview. You don't see it that well on the projector. This is 3 different galaxies seen from far UV, optical, mid-infrared, far infrared, and millimeter. How the galaxy would look in these different wavelengths. And you see directly, you see a difference in the morphology. So the galaxy is rather extended in the UV, becomes quite compact in the near infrared, and then spreads out again in the far infrared submillimeter. And we tried to measure that or quantify that. And this is what we call non-parametric galaxy morphology. So you measure a number of indices that describe the morphology of a galaxy. Now, galaxy morphology, there's so many different things you can say about the galaxy, but these are some of the most important ways to do that. First, you look at the half-mass radius. That gives you an idea of the size of a galaxy. This is, top right is the concentration, tells you how concentrated your emission is. This is the symmetry, and this is the smoothness. And what you see in blue is the multi-wavelength morphology measured in a set of observed galaxies from the Daspedia sample. And then red and yellow are measurements based on our skirt simulations. And you see, in general, that is not too bad. See, both observed and simulated galaxies are extended in UV. They become more compact in the near mid-infrared, and then gradually they grow in size towards submillimeter. And you have that also for observations and for simulations. Also, the concentration symmetry broadly is consistent, but we do find some differences. For example, here, our galaxies are way more asymmetric than the galaxies that we observe. So there are some differences that we cannot yet explain. This is work we published earlier this year, is the TNG50 skirt atlas. So that is a large multi-wavelength atlas of synthetic images. So we looked at more than 1,000 galaxies from the TNG simulation, TNG50, so the highest resolution TNG simulation. Essentially, why 1,154? It just we took all galaxies within a certain mass range. We ran skirt on them for months. We created images in different bands from 5 different viewpoints. We made physical parameter maps at high resolution, 100 parsec resolution, and very wide field of view. So you have these like very large data cubes. See a number of examples here. All these data are publicly available. If you're interested in playing with mock images, you can go to the TNG data archive. And this is like a zoom of one of the images where you see you have images here, U band all the way to K band in near infrared. Then you have also stellar mass map, metallicity map, age map, dust mass map, as you can try to compare these observed images with the intrinsic properties. Now, one of the things we did with these galaxies is looking at the effective radii of observed galaxies. This is work already more than 10 years old, Kelvin and all, showing that the size of galaxies depends on the wavelength at which you measure it. So galaxies appear larger in blue light. So blue light, if you look in the near infrared, they become very compact. That's been measured. Now, it argued that this that there's two reasons why this could be the case. One of them is gradients in the stellar populations. The typical image of a galaxy, of a spiral galaxy, you have a blue disk, you have a red bulge, and of course, if you look at redder wavelengths, you primarily see the central bulge, so it appears relatively small. If you look at blue wavelengths, you mainly see the disk, and it is larger. Okay, so it's a natural way, if you have stellar population gradients, that your galaxies appear smaller in redder bands than in blue bands. Now, the other effect is dust attenuation. Because if you have dust in your galaxy, it will preferentially eat away the blue light. And so the more dust you have, the more blue light is taken away and only the red light remains. Now, dust is primarily concentrated in central regions. So by eating away the blue light, you essentially make your galaxy appear larger because the outer regions will dominate more. And so both of them result in the same trend. Now, for observed galaxies, it's very hard to discriminate between these two mechanisms. What is responsible for this trend? But of course, for simulated galaxies, we can do that because we have the 3D distribution. So what we did is we took all of our images, determined the effective radii for all galaxies at all different bands, and plotted it as a function of wavelength. And indeed, we found actually the same trend that galaxies are or appear larger in blue band, and they are smaller or more compact in the near infrared. But we can also do that for dust-free images, because we also have the images without dust. And then you get the blue curve, and you still get the same trend. The effect is slightly smaller, but it's still there. And of course, in the blue line, this cannot be, the origin cannot be dust attenuation. So indeed, that is due to stellar population gradients. And if we quantify that, we find actually that 80% of this trend with wavelength is due to stellar populations, and dust attenuation is responsible for only 20% of this trend. Which might be interesting for people who want to correct their observations for dust. This is the UVJ diagram. It's like a diagram where we put galaxies as a function of rest rate color. So this is UV optical color. This is an optical near-infrared color. And so every galaxy, the whole population of galaxies is plotted here. And this diagram is often used to separate star forming from early type galaxies. And typically people use a region like this. Everything that is here is an early type galaxy. Everything that is here is a star forming galaxy. The reason is that galaxies move, if you have more and more dust, they move perpendicular to this line and they keep out of this region. And you see that here, what the color shows the specific star formation rate. And of course, early type galaxies have a very low specific star formation rate, and they are all in this top region. Now, it has been argued that some of the quantities in this UVJ diagram also correlate with specific star formation. So you can also use the position of galaxies in this diagram to extract other properties of galaxies. And also one of the things we can do is look at the effect of dust attenuation. Like we can have our naked colors and then see where the galaxies end up after dust attenuation is included. And that is what you see here. So these are the same UVJ diagram, but now without dust. And you see galaxies form a much tighter sequence. These are the early type galaxies, and these are the star-forming galaxies. Now, if you add dust to them, they tend to move indeed in this direction. See, now they start to populate this entire region. And we can color code that with different physical properties. And one of the things that we found quite interesting is if you take The median, this is inclination. In every bin, what inclination is average. Median is like 45 degrees, it's median inclination. But if you do it in this diagram with dust, you see that the ones that are on the right are all almost edge-on galaxies. Because if you're edge-on, you have way more dust attenuation, and then you move your galaxies towards that direction. And also, many of the galaxies that are reddened by dust actually end up in this early type galaxy region. So here there's no galaxies, here there's all galaxies that end up here. And so dust attenuation pollutes the early type galaxy region with galaxies that are actually actively star-forming galaxies. And so you should not blindly trust this UVJ diagram. We also looked at this same diagram on sub-kiloparsec scales, because you can look at the global colors, but you can also look essentially at every pixel. And we have a lot of galaxies, and for every galaxy, a lot of pixels, so that we end up with millions of pixels. And so these are the same global properties of the galaxy population. If we look at the same UVJ diagram now per pixel, you end up with a whole, it essentially fills the whole parameter space. And we still don't understand this. So this is something we are still working on, and we have to think how it's possible that galaxies can be quite blue in this V minus J color, but quite red in the U minus V color. So there is something that is still escaping our understanding, and we have to look at it a bit more carefully. All right. Are you still awake? Okay. Last thing I want to say is to use H1 as a test of galaxy formation models. Because H1 is actually quite interesting. H1, you see it with 21 centimeter radio observations. And that's an interesting probe for these kind of simulations because it is not used in the calibration process. So these simulations such as Eagle or TNG, they have a number of free parameters and they must tune them. And usually they are tuned to make sure that the galaxies they end up with have the right stellar mass distribution, stellar mass function. H1 never comes into play in this tuning of the subgrid recipes. So it's completely independent of that. And as such, it's a very independent test. And the second reason is that there is a big revival in 21 centimeter observations. I don't know whether you're aware of that, but they're building new radio telescopes at different places around the world. And this, for example, is at this moment the most powerful radio telescope there is. This is the Meerkat telescope in South Africa. It's a precursor for the SKA, for the square kilometer array. So there is now really excellent data coming online. There's still a challenge that the 21 centimeter signal is weak. So you need huge collections of dishes to get 21 centimeter. And if you want to go to slightly higher redshift, you are limited to going to redshift 0.2, 0.3. We hope to reach redshift 0.5, ultimately with the Meerkat telescope, but that is, it's not like with James Webb that you find redshift 12 galaxies in H1. It's impossible. But still, it's a very nice test for the local galaxy population. Another challenge is that atomic hydrogen is not predicted directly from your simulations. Your simulations predict the amount of gas or the amount of neutral gas, but it cannot separate between atomic and molecular gas. Why not? Because that depends on the radiation field. Your UV radiation field will determine your balance between atomic and molecular gas. It can dissociate molecular hydrogen. But that is something we can calculate with SCIRT because we can do radiative transfer. We can calculate everywhere the UV radiation field, and then we can split it, the amount of gas, into atomic and molecular parts. And so we have developed a methodology to do that, and then we can calculate H1 maps or synthetic H1 maps for simulated galaxies. Like this is like these are real galaxies, and these are then simulated galaxies from the TNG50 simulation. And globally, they look a little bit similar, but not completely. One of the things we find is, for example, that the TNG galaxies, as you see there, often have holes in the center. And some observed galaxies have that too, but we find way too many holes, which tells us something about the AGN feedback. Probably the AGN feedback is way too heavy in the TNG simulation. But we then, again, can start to compare observations to simulations. And what you see here on the left, for example, is the cone density distribution function. It just how many pixels on the sky do you see with that much of H1? And you see in general, these are the observations, the gray. This is what comes out of the TNG simulation. Not perfect, it's not too bad either. But there's still improvements that are possible. And one thing that I've been working on is the Tully-Fisher relation that I already indicated before. It's like a relation between H1 profile width and the optical luminosity, meaning that more luminous galaxies have a broader H1 velocity profile, which is not expected a priori because the optical luminosity just tells you how many stars you have essentially. And the H1 alignment is determined by the dark matter halo. So the galaxies have a flat rotation curve, which we find that is driven by the dark matter halo, and that sets the H1 profile. So this Tully-Fisher relation probably suggests a tight relation between the dark matter halo and the stellar mass distribution. Some kind of conspiracy that the dark matter halo knows how many stars are being formed in the halo. And it's not that trivial that simulations reproduce this. There's a lot of studies on the Tully-Fisher relation. And one of the things that is found when people did studies like this is that if you go from blue bands to red bands, you always have like a correlation between these two properties, but the relation gets tighter and steeper if you go from blue bands to red bands, meaning it becomes steeper and you have less and less scatter. And that is something we wanted to try to find out. So again, we used TNG50 to calculate the Tully-Fisher relation, calculate the luminosity in every band. We calculate the H1 light line profile, we measured the width, and we plotted them against each other. And here you see the results. And you see by sides, it goes from UV all the way to the near infrared, that the scatter is here much, much larger than it is. It's much tighter. If you look also at the slope, which you cannot really see on this graph, but if you quantify that, it also becomes steeper. So this is slope that we find. This is the slope by some study that did a similar approach on observed galaxies. And you see, our slope is, our dependence on wavelength is a bit less outspoken than it is in the observations, but we're not that unhappy with that. If you look at the tightness of the relation, like the bottom plot, like how tight is the relation, it's embarrassingly in agreement with the observation. So I was almost thinking I plotted the wrong quantity, but this is what we find, and we're pretty happy about that. Good. Now there's more tests we plan to do to look at morphology, to look at scaling relations, but I have to come back, I've heard some other times, so I'll tell you more about that in the future. But I want to tell something more about other things you can do with skirts, things we've been working on in the past years, because it started as a dust radiative transfer code, but it's now developed into more generic Monte Carlo code. And one of the things we've been working on is X-ray radiative transfer. So we have implemented what we think are all the relevant physical processes in cold, dust, and gas. So that means absorption by atoms, fluorescent line re-emission, quantum scattering, and so on. We've tested this through various AGN torus models. So you see the black line there is skirts. The orange line is another 2D model called reflex. And you see we agree very well with the lines at the right place and with the right strength and so on. So it works pretty well. And so the advantage that we have is we are now completely 3D. So we can use all the mechanisms that were already in SCIRT, all the grids and the panelization and so on. And we can make, for example, post-processing hydro simulations of AGN tori with all the full details. And what you see on the bottom right is like a 3-color X-ray image of one of these torus simulations, where you see that the hard X-rays are the ones that are here, and the soft X-rays are only the red ones because they only can leave the system away from the torus. So you can have these things, which is nice. We've been working on resonance scattering, so that is Lyman-alpha radiative transfer, where we put all the standard ingredients. We reproduced the benchmark, so that works well. But if we tried to apply it to galaxy simulations, actually we encountered issues that actually the results, we always had results, that was not a problem. But the results depended very sensitively on how we grid the thing. So if we use an octree grid or a Voronoi grid with twice as many cells, the line profiles can really change completely. And if we just have dust, then we have exactly the same results. If we have Lyman-alpha, the results are very sensitive to how you put your grid cells. And that is, we believe, is due to very large gradients in the hydrogen density. Because if you have such a simulation from one cell to another, it can differ with 4 or 5 orders of magnitude. And then depending on how you interpolate on that, your results can be completely different. And we tried the same thing with another Lyman-alpha code, and actually the same thing happens. So our conclusion was be very careful in trusting the results of any Lyman-alpha radiative transfer code, because it's very sensitive to how you discretize this. The last implementation we had is line radiative transfer. So it's transfer in molecular and atomic lines, like CO and C+ and OH and so on, where this becomes a bit more challenging because you iteratively need to go over your level populations and your radiative transfer. Because your level populations depend on the amount of radiation, and your radiation depends on the level population. So you need iteration, which is only possible if we have big computers. But the nice thing is we can also now include line radiation in, say, 3D structures like, again, this AGN torus, and we can predict dust continuum images like we see here, ALMA and James Webb images, but also like images that look, for example, in different CO lines, and then predict how the line profiles differ in different transitions and in different inclinations. So we believe this works pretty well, and you're welcome to use it. So the last thing I want to say is SCIRT is open source, so anyone can use it. Anyone is very welcome to use it. I'm very happy that people here actually do use it, so please continue doing that. We hope to have implemented some things to help you with that. So we have user-friendly interfaces, we have documentation, tutorials to get you up to speed, and we have a toolkit to help you analyze and visualize your results. So if you have things that are on your wish list, talk to us and we can try to get that. And even more important, or at least as important, is that SCIRT is also open development. So everyone can contribute to SCIRT. also you're most welcome to do that. If you help us, there's a developer guide. If you say, I want to implement this, or want this feature extra, or hear a bell, or hear a whistle, please you can try it yourself, and we will also guide and support you as well as we can. But so you're very, very welcome to do that. And this is where I want to end. So I hope I argued convincingly that an apples to apples comparison between models and data is useful. Just leave it here. And that SCRT is a general purpose multi-physics radiative transfer tool, and please do use it or contribute to it. Thank you. Questions?
Okay, first of all, thank you very much for the work and for your support, because I have many questions, but one that puzzled me was, you mentioned that like Lyman-alpha is the more sensitive to the grid size. Why is that?
Because,
any particular reason?
yeah, one, because the densities in hydrogen are typically orders of magnitude more larger than the densities in, say, dust from cell to cell, and also because the optical depth of the Lyman-alpha line is extremely large, and the variation from core to center is really orders of magnitude. And so if you have two cells that are different in density and in velocity, if you interpolate between them, you get completely different line profiles and completely different optical depths. And so it is very, very sensitive to that. And that's much less so in, say, dust or X-ray radiative transfer.
Do other tools report the same sensitivity when they look at that?
They haven't done that. So we work together with somebody who has his own code, and if he ran his own code on a similar problem, he found the same thing. So, to be honest, I'm not that familiar with the recent research in Lyman-alpha. It's not our key expertise, but as far as I know, no one has shown us wrong at this stage. So I have a hard time believing that the results we have are due to some error that we made. So I cannot. I think it's a real problem.
So do you have recommendations for like next hydro cosmos simulations and what they should do better than from your analysis on SCRT? So you mentioned AGN feedback. But...
Well, I'm not the only one they should take lessons from, but I think most of the things that we found are already known, are a little bit the weak points in the hydro simulations. And the one is AGN feedback, which is very hard to pinpoint, because it's, if you look at AGNs, they're very complex systems, and sometimes in most hydro codes, the feedback is just thermal or kinetic feedback that is somewhat isotropic, but we know there are jets and so on, so that is much more difficult to model. And the second one, and that's something that new generation of hydro codes are working on, is modeling the multi-phase ISM. So most of these big volume simulations, such as TNG and Eagle, use like a single ISM phase. They have a temperature floor about 8,000 Kelvin, and everything below that is like done with a calibrate recipe. Now, the more recent simulations really do multi-phase ISM. So they go down, they have cooling functions all the way up to 10 Kelvin or so, which is much more computationally demanding, but the new generation of simulations will be much more powerful in that respect. So that's something that I'm very curious on applying skirt to them. And if I may add, the next generation also typically will have dust recipes in them. So they also have a dust evolution model where they have dust grain growth and dust destruction and so on included in the hydro simulation. So now we have to like invoke the dust using some recipe, but that will be part of the hydro output in the next generation. So that will be take away some of the biases that we put into it at the moment.
So what about dust? What do you consider that are the main constituents of dust? The spherical particles?
That is something we have, the user can choose to put in. So if you have a hydro simulation, typically the only thing you have is the gas cells and some properties of the gas cells, like the density and metallicity and so on. What we typically use is a recipe to then say how much dust there is in that cell and what this dust consists of. And we typically use a physical dust model like the ARTEMIS one that consists of carbonaceous grains and silicate grains with a certain size distribution. But that is, there's very few constraints on that.
Such that they are spherical or ovoid?
We depends on what you have. If we want to have like these broad bands SEDs, we use spherical grains. We also have polarization and dust polarization into a model. Then, of course, we use a model with spheroidal dust grains. And we have compared that, for example, to Planck, the polarized galaxy emission, dust emission, and that agrees to some degree. But again, you have to put in something and some alignment mechanism where the dust grains are aligned. But again, there's a lot of freedom there to do what you want.
So, but this is allowed already in the code. I mean,
it is allowed in the code.
An option.
Yes. Yeah. One thing we do not have is dichroism. So like the polarization of optical light due to dichroism, because that's really hard to do. But it's on our wish list for a long time. So if anyone with an interest in polarization wants to contribute to skirts, he or she is more than welcome to do so.
If you enjoyed the video, like and subscribe.